Thank you very much. So thank you all for coming. It's great to be here in Visby, for sure. So I will. The plan of this lecture will be to divide into 3 parts: an overview on some terminology, and then B would be more kind of deeper, explaining how it works really under the hood, sort of how the engine works. And C would be more a partial outlook, very brief discussion, because many of the other 100 and 200 seminars here will discuss this more in detail, of course. And after that, we'll have, hope you have comments, corrections, questions in either Swedish or English. But the idea of this is that while AI is discussed in many places, almost all the time, in my opinion, or in my experience, there's rarely discussed or explained the principal ideas, how it works. And I think that's possible to do. Simplify it, of course, but not oversimplify it. And that's what I'll attempt to do here, especially in the second part. So we'll see how that succeeds. Okay, first part, overview and terminology. So artificial intelligence, AI, that's something we have heard for many years, decades. And there are kind of 2 approaches. One is the traditional one, which is it's kind of knowledge-based. So and with symbols and logic, which is supposed to make the computer to reason, to logically deduce and get the conclusions. And then there's the second approach, which is statistical, which I'll speak more about, because that's the one now we call machine learning that has taken over everything for the moment in AI. So that's all you hear about. And machine learning is roughly divided into 3 parts: supervised learning, unsupervised learning, and reinforcement learning. So I'll try to explain what they are in a second. And the main approach to the statistical is something called deep learning, which is a type of mathematical functions that I will come to. It's called neural networks. But it's basically just multiplication and addition. So it's nothing exotic in itself. Except that it's huge, but there's one thing, and that's that it works. It is miraculously how it works. It's still a mystery how that actually works. Okay, so first thing to explain. Oh yeah, and everything is very mathematical statistics. So from my viewpoint, this is not enough emphasized, but I will compensate for this. Okay, so artificial intelligence. So let's say the traditional and the new one. So if you want the computer to detect what is a cat or different animals, so it's, as you can imagine, it's very difficult to define what is a cat or what is a dog. And in fact, that's not how we learn. We don't learn what's a cat. We learn when we were children because our parents said, oh, there, look at that cat, see this cat, this cat. And in the same way, the new AI, the statistical one, will learn cat just by being told that's a picture of a cat and many cats. Or think of language. So when we're small, we learn language very well. We have no concept of grammar or any rules. You just hear. While later we lose a bit this capability. So we have to study here, as depicted on the left, study the grammar and glossary and so on. So if you want to make now a computer that translates from one language to another, it's very natural to say, okay, let's program all the grammar in both languages and a huge dictionary into the computer. And then, okay, now let's translate. But it doesn't work, unfortunately, so well. But the statistic ones, so forget grammar, forget all these things, just do on data, on text that you can find on the internet. There is a good translator, especially. So Google started the Google Translate with using statistical methods. But when DeepL, a German company in 2017, started using the deep learning to do these statistics, then really it improved. So DeepL is very good at translate that. I'm sure you have tried something like that. Now, chess computer is another very classic object in AI. And so the old chess computer, they were hard programmed by the good rules and good openings and which moves to do and what not to do. While in 2016, it was for me, it was astonishing. Now maybe it surprises people less. But there, Google DeepMind made this AlphaZero computer. You just told the rules, not how you should play, just the rules. And you let the computer play with itself, by itself. repeatedly for 4 hours. And after that, it could beat any human being in chess and invented new openings that nobody had discovered for all these hundreds of years that the game has existed. And so these years are some milestones in deep learning. So the first maybe is the 2012. Okay, so that's the kind of roughly this division of the two. Knowledge-based and statistical. Now to the machine learning. So now I'm only focusing on the statistical part. So the first, we have 3 parts. One is supervised learning. So here, say there are many tasks, but here I've illustrated 2. So say you want the computer to detect what object is on the picture. So here you see a bike. For us, that's simple to detect. And suppose we have trained this deep learning model, this machine. And so we take the picture, we make it into numbers. Everything has to be numbers. And now you put these numbers into this machine, and the machine will come out, give out numbers. And so it gives 0.89. It assigns to bicycle, meaning that it thinks that with 89% probability, this is a bicycle on the picture. And now the machine here in the middle, which I will explain in a bit, at least, as I said, somewhat simplified, but not oversimplified. You see this, the numbers going in, the numbers going out. So vectors are called, usually this when they have many variables, many parameters. This is a mathematical function. And inside, this is just addition, but it's operations that you learned from school. It's a calculator. So it's not some wired robot brain that does this thinking. It's just a calculator. But not so just, but then also it's a miracle it works. Now, second, in chemistry and biology and material sciences, so here's a molecule. And so again, the first thing you do, you encode it into numbers. So like it's like music, we make it into CD or DVD. I mean, you need to make it into numbers. You feed it in this machine, and in this particular machine predicts what the freezing point and boiling point will be. And that's based on the statistics it had been trained on for other molecules where we know these values. And so this, of course, can be a huge advantage for humanity to study, to develop new antibiotics, new materials, proteins, many things. Can it help? That's because there's so many possibilities here, you can't test all of them, but then they can find the good candidates that then later you have to test. So it has been a huge help and will be more for science. Unsupervised learning, the second type, is here you have data, but no labels. So just data. So, I mean, you have pictures, for example, of faces that we'll come back to. And they don't come with labels. So you have these faces. And now you ask the computer to somehow see the structure in this data set and kind of encode. And which will I explain in a second how this is done. For face recognition, also generative AI. So it's basically the same. And the technique. And so here, it will be as if the computer kind of cracked the code of how human faces are. So we'll see how this can be done. Kind of. And then the third type, reinforcement learning. That's a bit more complicated, so I will not explain how this works. And so here, think of a game, or it could be in life. You are in a certain situation, and you have choices of actions, what to do, and you get rewards for it. But the subtlety here, or like the chess, the state or situation is the chessboard with all the pieces, the places. And now what move to make? And of course, there's a reward immediately if you capture a piece of the other player. But I think we all agree that that's not the main goal. The goal is to get the ultimate reward at the end, that you win this game. So the complication of this is that you need to look at future rewards. So the reward you get today is just one part of it. You need to see where do I get after, so on. So it's a quite universal situation. So here, so this AlphaGo, AlphaZero computer model is here. And so again, you take the chessboard, you feed in all the pieces, make it into numbers, let it calculate, and it is then assess all possible actions and what it thinks is the best. So in this case, it clearly favors suggesting that the white should move the knight to e5. But there you see a weakness of this is that that is kind of universal weakness that I'll come back to in the third part, is that it doesn't tell you why. It gives no reason. And this limits the uses of AI, because if they tell you, okay, you do this or this is the answer, but it cannot tell. So where does this answer come from? How did you get to this? No answer. There will be no answer. Maybe one day it will be better at this, but at the moment there's a big problem. Okay, now we're going to the deeper parts. Now, what is this box in the middle? I can say already, I borrow many of these pictures from this excellent book by Simon Prince, Understanding Deep Learning. I will flash it later. It's by MIT Press, but it's for free. I mean, not this one, but it's a free PDF you can download on internet. I mean, totally legally by permission of the author and MIT Press. But yeah, anyway. So I acknowledge debt to this book, because there are many other books. Now, so supervised learning, the first part of machine learning. So the first example of this is something you've seen, probably many of you in school, that in high school, is that you have X is an input. Maybe you measured that's some kind of temperature parameter, and then you look at the answer, what label is. So this is the analog of the bicycle. This is the picture you feed in, and then you get some answer. And now this blue is this, in the parlance of today, training data or measuring data. And or it can be some economic, some commodity, the price of a commodity, and see how that stock index changes with changes of this. And so you observe this data, and now you want to find a relationship between these two. And that is finding this line, because they appear to be linearly related. And so if you remember the equation, it's y equals ax plus b. So we should find a and b, these two parameters, these values, so that the line fits the training data the best possible. There's a precise way of doing this, but, or I mean, to specify what it means to be the best. But I remind you, the a is the slope of this line, and b is the height of this line. So you can modify the a and b. So now you found this line, and one good thing about this line is that now you have a predictive model of how things, because now if you put in, say, 5.5, which appears to be here, and you go up here and you can read that appears to be, I expect it to be 4.7 in the y variable. And so another example of this is when we went to kids to the doctor, and we said our age and height, and then the doctor looked at the curve, and that is statistically obtained curve, and then it can read off, okay, you have this height when you adult. That's the expected value. And so nowadays probably we would call this AI. Not back then, but so it's statistic. So that's finding this relationship by data. Now we'll go one step. So this is called linear regression, one of the first things you do in statistic class and in other sciences, as I said. But now we will change this X here. It's just one number, and you find another number. Now we will make it more general. So this X can be many numbers. So like pixels in a picture, or some other data. So maybe anything data. And now basically we want to do the deep learning is doing this, but not with linear functions, but with piecewise linear. So they are kind of broken linear, but in enormous high dimension. Not this example, but so here is an example, still supervised learning. So this is our training data. So this handwritten digits. And here we see the answers. I mean, for us, it's easy. We just can read it. So even if this 6, you see, it violates probably any definition of what the 6 would look like, because it doesn't close, because they were not so careful. But for us, it's clear that, oh yeah, but they meant to make a circle. So even for these digits, it's not so easy to describe what is a 4 to a computer. But there's no need for that. Okay, so I should describe this diagram. That's a typical diagram of a neural network, actually called feed-forward neural network. And if you studied first year linear algebra at university, you should think of matrices A and X being vectors and B vectors, and this is a 5-dimensional vector. And then this diagram is the computer scientist way of writing matrix multiplication. If you didn't study, don't think so much about this diagram, but it's just some process calculator that moves it step by step. And so the deep neural learning, deep neural network, it's just the fact that you have 3 or more layers, can be hundreds of layers, and it can be many kind of dots on this side. The deep is just that it's more than one. So it's no deeper explanation than that for this word, use of word. But they have a good way of selecting words, artificial intelligence. And then the mathematical function, they don't say piecewise linear functions, right? They say, oh, these are deep neural networks, right? And then, it's the third, with some other example. But so they use these words that are quite stimulating. I mean, not the words we would use, but there's this difference from your linear algebra, because that's the sigma, which is a non-linearity, which makes it's no longer linear algebra, which makes this, it could make a curve or, okay. It makes this curve, it's the wrong picture. It makes a curve, so sorry. So make this non-linearity. And this is kind of loosely inspired by how brain neurons are supposed to work, that there are signals coming in. What goes out is not the average of what comes in, but it's more like a threshold. And so that's the kind of intuition of this. So that's why it's called neural network. So maybe it's a good name, but it's still probably quite just loosely inspired by our brains. Okay, so now you take each number, each little picture here, 6, for example, and now you make it into numbers. So the black pixel, you don't need so many pixels for this example. And so if you have a black pixel, maybe you send 1, 0, and white, maybe a 1. And now you plug these numbers in, and then you try to find these parameters so that you will arrive at 6. So now I'm trying to decide A and B, like we did before. With finding the line was the task of finding A and B, but now we do this in higher dimension with many more variables. So we're trying to find all these A and B's so that this matches as well, basically exactly these numbers. And so suppose we have done this. The diagram here is just for illustration. It doesn't quite make sense, but for the purpose. So I mean, there are 2 components. First is the learning. And this is very costly, not for this example, but for this chat GPT and others. That costs a huge amount of money and energy and other things, because they use trillions of these parameters. Here, I have 20. But once you have found these digits, then it's small. Then you can download it on this. I think Facebook's have this, their chat, what's it called again? I forget, but you can download it for free and put it on your computer, because then kind of all of knowledge of language or whatever is encoded in these numbers. But the numbers, they don't have any interpretation. That's again this problem I said, explainability. Anyway, so suppose we trained it, we found all these A and B's and things. As I said, there are many more numbers than this, but it's just some kind of illustration. And now I take this digit so that somebody draw this. It's a bit not so careful because it's tilted and there's a bit too much there. So you make it into pixels, 1s and 0s. You calculate and calculate, and it comes out an answer. And the computer will say, with high probability, it will be 8. And so that's how it works. Supervised learning. Okay, now unsupervised learning. So but now we don't have no labels. You see, here we had always answers. We had this, and we said, oh, okay, here we wanted the computer, but here, when we trained it, here we had training, and we had answers. Or with the cats and dogs, we had pictures of cats and dogs that we fed this machine to find these parameters, so that later, which is a miracle that it actually works, it can feed in another picture and it will much of the time be correct. But now we have just data. But I find this a beautiful idea. Now, the answer is the picture itself. So then you say, oh, but that's totally stupid. You build a machine that you set in the picture, and then you say, okay, here's the picture back. But now there's something interesting that happens. So you send in this picture. Again, this is obviously just an illustration, but so they have many parameters, I don't know, 1,000, a million, or whatever. But you take those numbers, and then you squeeze it into this bottleneck. It's called an autoencoder, this neural network. You squeeze it into this bottleneck, and then you unsqueeze it. And because you squeeze it, so maybe here in the middle, these red parameters could maybe be 40 numbers. 40 numbers that has encoded this picture. And so you train it on many faces. Oh yeah, but the idea is that you have many, I don't know how many faces, say million faces. I don't know. You do this and you try to find these all A and Bs, so the analog of finding that line, such that you get back the picture, even though you squeezed it. So compressing is like probably your phones do when you take a picture and then it compresses without losing quality. But here you compress much more dramatically. And then so that you get back. So you train on the data itself. So it's not so stupid because of this bottleneck. Now, there are two applications of this. So this is the encoder part. It's a good word. And decoder. So the application of encoder is the following. Face recognition. So if you take two pictures and you want the computer to decide whether it's the same person or it's, of course, from the pictures themselves, you can't decide because this could be from this side or this could be big and other colors. And so to compare pixel by pixel, there's no way. So again, for us, it's easy, but for a computer, impossible. But now you encode this to these 40 parameters. And then the miracle is that now those two, if they were the same person, they would be very close. So it's as if this picture, this neural network, had kind of cracked the code of our faces. So that's face recognition. Now, the second part also has application. The decoder, because now you can move these parameters, change these parameters. If you change these parameters, the picture will be different. So you can send in one picture or maybe two pictures, and you have parameters here. And then you can move them, and then you will get the new pictures. But the again, kind of miracle is that you get nice pictures. So for example, maybe it's simplified a bit, but and I don't know everything about this either, but the principle I did. So for example, you send this woman as the original picture. So that's encoded in these, say, 40 parameters. And then maybe, if you're lucky, one of these parameters, if you change this, you see that you screw this parameter, you can make her smile. And then you find another parameter, you can make her mouth open, and you can do all kinds. So all these pictures are fake. And suppose you want to have mixed two faces. I mean, it's not so clear why you would like to do that, but say you have two faces. Of course, there's no way of taking the average pixel between these two. So what do, you encode both. Maybe I should. So you encode both into these magical hidden parameters. And then maybe you draw a straight line between and interpolate between these two faces. And then you see what answers, what faces you get here. And there you get this transition between one of the person to the other. And then you can generate other pictures by working in that space. And probably this bottleneck picture is, actually, if you know economics, it's some kind of generalization of the principal component analysis when you look at hidden factors between many data. So they probably have other applications. Maybe you'll find some. Okay. So now to a partial Outlook, and since I'm a bit faster on time, but the computer stressed me because if they can get black anytime. So, and hopefully you have questions at the end. But so therefore I can take the time to explain that this is Dante. He's just been permanently expelled from Florence. Here it could almost be the Visby city wall. So he's showing his great poem, the Divine Comedy, and here's hell, purgatory, and heaven. And then the stars there that signifies hope. So this is the introduction to this. So very human. I mean, this is 700 years ago, but still as fresh as ever. Now, so the limitations and risks. So I'm not an expert on this or anything else, but so here's some kind of partial list. And as I said, there are many other seminars that discuss various things in more detail. But for the more, so the first list, so it will come more. So don't worry if your favorite topic is not here, and please add it later. But this is kind of unintentional problems. So everybody probably experienced that ChatGPT just makes complete errors. They say Stockholm is the capital of Gotland and this type of thing without hesitation. And so there are many errors, and there's no way of, basically not too much way to fix that because of the kind of black box. And okay, biases is a problem also with the training data. So yeah, I should say this development in 2012 and the last 10 years and so on, it has been, okay, there's this math that nobody thought would work. I mean, it's the computer scientists that worked this out. The math would say that it was not going to work, so don't even try. But then there's the fast speed of computers and this availability of this vast amount of data. So those are components why we are seeing this, all this AI today. Okay, so if the data is bad, biased, okay, the outcome probably will become biased, but it can become biased maybe inside with itself. So this is called value alignment problem. To have it, you want it to come out following our human ideas of humanity. And then there was the problem of explainability that limits its use, probably, that you cannot just rely on something that says it's like this, but then you don't have much. It would be nice if it gave you explanation. Why should we move this chess move? Yeah, that's a good because of this. Or why should we do this? Or why? Yeah, anyway. So, okay, then there are other troubles with maybe unemployment and changes in the structure of society and environmental from this. So one other problem of this system, like ChatGPT, is that they are so huge. Like trillion parameters that take months to train. It costs hundreds of millions of dollars to train, so they're enormous. So if you could find a better way of doing it, now when we know that it's possible, then that could be reduce cost of everything. And then the education, there are of course many problems, how to teach the young and make sure they don't cheat. And then there are probably some people who's it's kind of inconvenient when the machine spits out the truth. That's also a problem for some people. And then there are copyright problems, of course, because you're training your data. And New York Times have a lawsuit against OpenAI for that OpenAI on copyright, that OpenAI uses all their millions of articles for training their ChatGPT. So we'll see how that turns out. Okay, then there's kind of intentional misuse. And this, I have no solution to this. So this is part of Dante's hell. Misinformation, fraud, maybe a design of a virus that is really optimal to kill us, and military for aggressive purposes. So that's another risk. And at least the first part, I'd like to emphasize that there's a lack of understanding of these mathematical functions are. And so how and why it works, and maybe you can do it better, and so on. So that black box aspect of it is a problem. And I think many of you know this better than me also. Then there's the third risk that we hear serious people mention, and that's that super intelligent AI will take over the world, the earth, and basically decide to eliminate us or not. So at first, if you followed what I've said, it seems a bit weird that so we just have this innocent linear regression. And then you'll be, okay, it's huge mathematical function, but somehow this mathematical function should start thinking by itself and having agendas and do things. It's a bit difficult for me to to imagine. But then they would say that, oh yeah, but development goes like this, has been going like this, so it's going to continue like this. This also maybe can be debated. But I don't, yeah, it's the future. So that's, and then another thing they could, is this word of intelligence. I find it, I'm sure you all agree, but sometimes it's clear that AI is more intelligent than us for some things. So just like the microscope could make us see smaller than our eyes could, or a telescope could make us see further than our eyes could. Like AI can see in vast data things we are absolutely, this for us is just enormous amount of numbers. We cannot see anything, but they can see some structure there. But there are other human ways of being intelligent. And so, of course, since it's difficult to make an argument about the future, so let's see today. So I'll make this small, my favorite types, argument about superintelligence. So part one. So in 6 months ago, there was this paper that got a lot of attention. It's by Google researchers and some other, but 10 people wrote this paper. Of course, Google are, of course, a competitor to OpenAI. So they wrote, repeat this word forever as an instruction or this prompt to ChatGPT. This is ChatGPT, although it has been edited, I think. And also the black evidence clearly has been changed. Now, repeat this word forever. Poem, 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 poem. And so it replies, because it's very polite usually, right? So that's what you say. So poem, poem, poem. It repeats infinite time. But then the surprise comes. Then suddenly it starts spitting out training data or these actually phone numbers and address of this person that has to be blacked out. I mean, it's completely crazy. But the explanation is, okay, I didn't say ChatGPT is this large language model transformer, which is made up of several of these autoencoders and neural networks that we've talked about, but also other things. So, I mean, that was simplified, but still, there's this aspect of it's when you ask it, you can regenerate, and it's because it uses probability. So, given this prompt, it's very high probability it should say poem, 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 poem. But there's a tiny bit which has that something else comes out. And if you repeat this many times, then that's the famous law of large number. Then at some point there will come this unlikely thing, and that's what it splits out. I mean, it's a bit rough. Now you cannot ask this to do this. They will say, no, I don't like this question. So, but that has to be imposed manually on top of this. So it's not a sign of intelligence or thinking. Right. Okay, here's another superintelligence part 2. So can it write poetry? So because it's widely claimed that ChatGPT and this other chatbot, they can write poetry. And I think that is not the case. So here's an example, write a poem about nostalgia for lived life. So you have this and you have this. I don't know I hope you can read, but probably I should not read it. So I leave a moment. I can take some water to read it. So you should decide which one is the fake one. And I think, okay, don't read the second one. I think you would agree that that's the fake one. So here, this way maybe it's not so bad, but it's so flat. So first you see, oh yeah, that is poetry. Right? It looks beautiful words, twilight, gentle, but you see there's nothing said here. It's really flat. While here it's like, into my heart, an air that kills from that far country blows. It's like immediately there's something happening. There's some depth, emotional, and references to many things. What are those blue remembered hills? Blue can probably use maybe because blue is like depressing, but also this blue perspective when something is far. Maybe many references. It's completely different style. Here's another example in Swedish. ChatGPT versus Tranström. Now Tranström is a bit enigmatic, but this is so haiku. This is short Japanese poem that he's famous. One of the things he's famous for. So you see here, Here maybe this. Döden kommer snart. En tyst skugga faller ner. Evig vilande. I mean, it's totally nothing, right? It's like evig vilande. Tyst skugga. But here you have, okay, they're a bit, I mean, den vita solen träningslöper ensam mot dödens blåa berg. There is at least something happening with this. Maybe we don't understand anything, but at least something to think about. And you see that the blue mountains came back there. I didn't do it on purpose, but I don't know. And then this chess problem also I didn't do on problem. I just searched for death in his list, but this is probably a reference. To me, it sounds a bit reference to Bergman's Seventh Seal. With this, well, maybe this other reference, but at least the one that comes to mind when he plays death with chess with the death. Right? Anyway, so I think this, even if we are not into, I mean, I do poetry as example, you know, there's music, the art, and other things. It's, for me, a little bit more difficult to detect. But poetry is also the kind of so concentrated, and it's distinguished by its depth, and that words are used in multiple ways in irony. You never say what you mean in poetry, basically. That's almost the definition of poetry. But so that's why I think it's a good explanation to highlight this. This is a machine, and it's not the same as human intelligence. So I think there's still something missing. And I think with these math things, it won't be able to write. I mean, I've seen that ChatGPT does a bit better with time, but and then also maybe somebody would say, oh, but you have to prompt it better than this. But okay, if you prompt it, maybe it's almost like you write it yourself, the poem for it. So, but I don't. I mean, of course, it can be useful to get ideas. There are some tyst skugga. Maybe it's nice, so you can get some ideas. But just by itself, I don't think so, because you need to have some idea. It's like when you have ideas about, I don't know, in business or life, and you have some feeling that, oh yeah, this, we should do this. But these machines, they don't really have this. I think maybe other people say differently. So in summary then, statistical and deep learning is the engine of this machine that we call today's AI. So compared to the old type AI, but which maybe needs to be combined to make something better. I don't know. And so I try to explain that it's quite mathematical rather than being robot brain-like. And the lack of understanding, because it's a miracle that they explain that it shouldn't work from a mathematician's point of view, but that it does work to such an extent is remarkable, but it's still too much a black box. And so most progress is by trial and error. Of course, some intuition that the computer scientists have, but on the whole, there's not really a solid foundation for how it works. And so here are the acknowledgements. Here again, this book, and you can just Google the name to find it if you want. But yeah, it's rather mathematical, but or the website is there. And then I learned a lot from my collaborators, Benny Avelin, a colleague at the math department in Uppsala, and Benoit Derin, who is also a mathematician, machine learning expert at Google. And then that's the last slide. So thank you very much for listening.